I will now talk about the concept of functions, which is basically mapping an elements of one set to another. And you have seen functions in other courses most likely, or maybe in school. But it's very important here to keep in mind the notion of functions that we define in this course. So we will basically define functions on two sets, A and B. Please pay attention to the two concepts here that are in blue. One is that both sets have to be non-empty. Okay, so A and B have to be non-empty. Each one of them has to have at least one element. Then we say that the function f from A to B, okay, that is from to, okay, so the function has a direction. We map elements from A to B. We denote it by f colon A arrow B. It's an assignment. We assign exactly one element from B to an element in A. Okay, so you look at every element in A, you go through the elements of A one by one. For each one of them, you find an element in B and you map that element to the one in A. Okay, so we write f of A equal B to denote that we have assigned the element B to the element A. Okay, so for example here I can define the function f from the set 1, 2, 3 to the set A like this, and I can define it as f of 1 equal f of 2 equal f of 3 equal A. Okay, this is a function. We mapped the three elements in A, which are 1, 2, and 3. There is only one element in B, and we mapped all of them to the same element. Okay, we can of course look at functions that we are used to. For example, f of n equals n squared, and let's say for example that we are defining it from z to z. Okay, so this is a function from all the integers to all the integers. So if you give me any integer n, of course n squared is defined, and this is a function. Okay, but for example, if you define f of n as the two square roots of n, the positive and negative square roots of n, then this is no longer a function, because if I look at f of 4, f of 4 is plus or minus 2. So now I violated this condition of exactly one element here, right? So if I'm mapping the element 4 to more than one element in B, and this is not good. So this is not a function. Okay, so again, it has to be defined on every element in A. It has to map every element A to a unique element in B. But please pay attention that by the definition of function, I am not saying that every element in B has to be used. Okay, some terminology about this, just because I just said that not every element in B has to be used. So what do we call the set of elements in B to which we map something? Okay, so if we have a function f from A to B, we call A the domain and B the codomain of the function. Okay, so we have the domain, we map the elements in the domain to elements in the codomain. If we map A to B, little a to little b, we call little b the image of A, and A the pre-image of B. The range of the function is the set of elements in B to which we mapped something. Okay, so the range is always a subset or equal to the codomain. Okay, the range or image of a function is always, so the range of a function is always a subset or equal to the codomain. But they don't have to be equal. For example, I can define f from z to z, where I say f of n equals 1. Okay, so in this case, the codomain is the entire set z, but the range is actually a very, very small subset of that, and it has just the element 1. So the range is the set that has one element, which is 1, because we mapped every element in z to just one element in z, which is 1. Okay, so the codomain is the whole set of integers. The range is really just a set of one element here. We have the notion of equal functions. So I can give you two functions and I ask, are these two functions equal? What does it mean for two functions to be equal? Two functions are equal if they have exactly the same domain, exactly the same codomain, and they both map the same element to the same element in their codomain. Okay? So we want, if we have f from A to B, G from C to D, A has to be the same as C, B has to be the same as D, and for every element in A or in C, because remember that A equals C, for every element in A, f of A equals G of A. Okay? Notice that this for all elements A in A, I could also have written for every element A in C, because C and A are equal. Now, here are two examples of functions that are equal. F of x equal x, G of x equal x, and think that I, for example, have both of them from R to R, from the reals to the reals. These two are equal functions. Of course, these are trivially equal functions. It's just the same function. I wrote it there, right? But here's an example of a function, of two functions that are equal, but they are not, this trivial example here. So let's define f from the set 0, 1, 2 to the set 0, 1, 2, and define g from the set 0, 1, 2 to the set 0, 1, 2. And let's define f of n to be n plus 1 mod 3. What does this mean? F of n, you map the element n to n plus 1, take n plus 1 divided by 3, and take the remainder. That's what we assign f of n to, or n to, sorry. And let's define g of n to be n minus 2 mod 3. So take n, subtract 2 from it, divide by 3, and take the remainder. Let's look at what the values of these two functions are. So let's see what f of 0 is. F of 0 is 0 plus 1 mod 3. 0 plus 1 mod 3, it's 1 mod 3, which is 1. F of 1 is 1 plus 1 mod 3, which is 2. 2, if you take 2 divide by 3, the remainder is 2. If you take 2, 2 plus 1 is 3, mod 3, it is 0. Okay? Let's look at g. What is g of 0? G of 0 is 0 minus 2, it's minus 2, divided by 3, and the remainder. What is the remainder of that? So how do we divide negative numbers and take the remainder? If you look at minus 2 here, I'll write it here. So I'm looking at what is minus 2 mod 3. If you look at minus 2 mod 3, the minus 2, it's minus 1. The minus 2, it's minus 1 times 3 plus 1, right? So it's minus 3. So we have minus 1 copies of 3, and the remainder is 1. Okay, so this is the remainder. So it is 1. What is g of 1? Let me erase this. The g of 1 is, if I look at 1 minus 2, it's minus 1. Minus 1 mod 3. The minus 1, it's minus 1 copies of 3. So minus 1 times 3, it's minus 3. I need to add 2 to it to get the minus 1 here. So this is 2, and similarly g of 2 is 0. So if you look at these two functions here, f of 0 equal g of 0, f of 1 equal g of 1, f of 2 equal g of 2, they both have the same domain, they both have the same codomain, therefore f equals g in this case. Okay, so this is an example of two functions that are equal, but not trivially equal, in the sense that they are not exactly the same function when we write them. The last concept I want to talk about here is the sum and product of two functions. It's a very simple concept. So suppose we have two functions f and g. They are defined from a set A to the real numbers. Okay, we insist on the real numbers because we need to be able to add the numbers and to multiply them. Okay, so I could not map to a set that has ABC because I don't know what it means to add letters. Okay, so think of two functions f from set A, whatever that set A, it's non-empty set A, to real numbers, and g is the same thing from A to the real numbers. F plus g, it's basically you take f of A and g of A and take the sum. F times g, you take f of A times g of A, and this is the product. So let's look at an example. Suppose I have two functions from the reals to the reals. Sorry, one is, let's say, 2x, and the other one, it's 4x plus 2. Okay, so these are two functions. What is f plus g of x? Well, it's just we take the sum of these two. So it's 6x plus 2. What is f times g? This is times here, because we will later see another symbol, which is we have the composition of functions. Okay, so this is product here, dot. F dot g, it is 2x multiplied by 4x plus 2, okay, which is 8x squared plus 4x. Okay, so this is what the sum and product of functions are.